Hey guys, Jake here coming at you with another math lesson today. Today we're going to be talking about optimization problems. Typically I do my weekly live streams at this time each week. My schedule's been a bit crazy this month, so I wasn't going to be able to live stream at the normal time, but I wanted to make sure to give you a nice similar long content where I dive a little bit deeper into a topic. So today we're going to be talking about optimization problems. Before we jump into an example, which I will get to, I wanted to just take a moment to kind of talk about the steps that an optimization problem is going to take you through. Now, these steps are going to be applicable for basically any type of optimization problem that you're going to need to do in like a calculus 1, like differential calculus course. So I think this is going to be really helpful for you because this is going to give you a roadmap that you're going to be able to use on basically any optimization problem you're going to run into. So when I say optimization problem, basically the type of problem that's going into that category, it's typically going to be explained by some sort of real world situation. Like maybe there's an area that you want to surround by a fence or a box that you need to make of a certain specification. Or sometimes it's even just going to say something like, pick two numbers where the product is as big as possible and they add up to a certain number. Those are all examples of optimization problems, and they all follow this exact step-by-step process. So the first thing that you want to do with any optimization problem, and this is probably good advice for any type of calculus problem or any math problem in general, first, understand what is being described in the problem and use that understanding to draw a sketch of what is happening. So first we're going to draw a sketch of the problem. Okay, so when you draw your sketch, you want to make sure that you're going to basically, draw whatever real world situation is happening. So if there's an area that you're trying to surround in a fence, you would draw the rectangular shape of the fence or whatever shape it's supposed to be. If it's a box that you're trying to build, you would sketch a box, right? So that's going to be, pretty much just drawing what's described to you. Once you draw your sketch, you're going to start labeling it with a few different specific things that need to be included in this problem. So you're going to label your sketch, but what's important is what you label it with. There's two things that need to be included in your labels. The first thing is going to be you're labeling whatever the thing is that you're trying to optimize. So basically, whatever the problem tells you you're trying to make as big as possible or as small as possible, or in other words, whatever you're trying to maximize or minimize, that quantity needs to be kind of referenced in your drawing. Of course, it can be difficult, like if you're trying to, maximize the volume of a box, for example. It's kind of weird to represent that in a drawing, but make sure that you do at least kind of label volume off to the side as the thing that you're trying to optimize. And I'll get into why that's important in the next step. But just make sure that you're labeling that. And the other thing that you're going to make sure to label is any measurements that you're going to need to use in order to find the quantity that you're trying to maximize. So for example, if we're looking at a box, you're going to need the length, the width, and the height of the box to find the volume. If you need to maximize or minimize the area captured within a fence, you're going to need the length and the width of the fenced area. And you're going to have to kind of logic out what quantities are going to be needed for that, depending on what is the thing you're trying to optimize. But whatever quantities you would need to know in order to figure out the quantity that you're trying to optimize. Okay. So once you label your sketch, the next step that you're going to do is to come up with an equation. Now, this equation is typically going to be an equation which is whatever this quantity is up here that you're trying to optimize. So typically, again, we'll kind of think back to the box volume example. Let's say we're trying to maximize or minimize the volume of the box. We would want our equation to just be, volume equals something. That's typically going to be the case. Maybe not always, but what your equation always is going to have is these quantities from the prior step. You're always going to have to include the quantity that you're trying to optimize, whether that's volume, area, et cetera, whatever that's going to be, you need that to be in there. And then you're going to use these other measurements that you need to calculate that optimized quantity also in your equation. So for example, I kind of brought this up before. Let's think, if we're trying to maximize the volume of a box, we would use something like volume equals length times width times height. For example, that's just a possibility. The exact problem that you're trying to solve will kind of give you more clues, but let's just go with, this as just kind of a vague example. Okay, so that's going to be one equation that you need to create. So keep in mind, this is going to be the equation that you're trying to optimize. So this is the one to optimize. Okay. Then you need to come up with another equation. This equation is, now this step is possibly optional. It really depends on what you get for step 3 here, your equation that you need to optimize. If what you did was create an equation that has multiple variables in it, like let's just take this one, for example, volume equals length times width times height, you're going to have to come up with other equations, which I like to call it a restriction equation. So what that does is it gives a restriction on the relationship between these other quantities. So create a restriction equation, or a few restriction equations, possibly, depending on how many variables you have. So typically the number of restriction equations that you need is going to be one less than however many variables you have over here. However many of these other measurements needed to calculate the optimized quantity that you're trying to find. So for example, if we had volume equals length times width times height, we would need to create 2 restriction equations in this step, because what we're going to have to do next, once we create our restriction equations, we're going to have to use that to kind of simplify this equation. I'll get to that in just a second, and that'll make more sense once you see an actual example. But what your restriction equations are going to do is relate these quantities. Like, for example, let's say you know that your box is going to be a square, or not necessarily a square, but basically some relationship between the sides. Maybe it has a square base, and there's some restriction on how much cardboard you have to build the box, let's just say, for example. Basically, you would have to use that, knowing that the total area of the total surface area of the box has to add up to some certain thing. So then we would end up with length times width plus length times height plus length times, or not length, sorry, width times height, all that times 2 to account for all the surfaces of our rectangular prism, have to add up to some certain number. Let's just say we have 100 cubic centimeters of cardboard or something like that. I just kind of made that up randomly, but that's an example of some sort of restriction equation. It relates these other 3 quantities, or 2 quantities, or however many you have that are going to be, not the quantity you're trying to optimize, how they're restricted. So once you've come up with these equations, then what you're going to do is you're going to solve your equation from step 4. So use your restriction equation or equations in order to like solve this for one of these variables and plug it into your optimized equation. So we're going to use equation from step 4, so number 4 equation, to simplify, or in other words, substitute variables out of our number 3 equation. Okay, so we're going to take this equation, solve for some of the variables, or take these equations and solve for some of the variables and plug them into the equation you get from step 3. So the goal here is to reduce this equation down to a single variable equation. So we need a single variable equation. Now, when I say single variable, what I mean is we would end up with like volume equals some function of width. So let's say we wanted to take this equation, take our restriction equations, and use those to basically solve for H, solve for L in terms of W, and plug that into this equation so that we just have volume equals some function with just W in it. Basically, we're trying to use substitution to eliminate variables from this equation. Once we get this down to a single variable equation, then what we can do is just apply basically first derivative test of, finding the absolute max or min value of the equation that we end up here in order to optimize the function. So then we're going to find the absolute max or min, depending on what the question asks you to find, of equation from step number 5. So we're going to take this equation and find the absolute max or min value of that over whatever domain actually makes sense. And when I say whatever makes sense, I mean like, thinking about what this equation represents. It represents a volume. It takes a length, a width, and a height. Length and width and height of a box are always going to be positive numbers, right? So we know that the domain is going to be restricted to positive numbers, positive W's, positive V's. So that's what I mean. You're going to want to kind of use the real world context to figure out what numbers actually make sense for the domain. And then you're going to find the absolute max and min value of this single variable equation within that given domain. Now, I want to show you an example of how to actually apply this. But this is all you really need in terms of the actual steps. So what you can do, if you want to, you can just take note of these steps and use this as basically a roadmap for any optimization problem you're going to have to do. So I'm going to go ahead and show you an example of how to actually apply these steps. If this is making sense so far, do me a favor and drop a comment down below. Just say, got it so far. And if you're getting some value out of this, hit that like button for me. It's a huge help to me and my channel so I can keep making more videos like this. But let's go ahead and get into an example. So I kept referencing a box that we're trying to maximize or minimize. The example we have is a box, so perfect. So let's say we have this problem here. A box with a square base and an open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. Okay, so like I said, first thing you want to do is draw the situation. We have a box. We know it has a square base, so we're trying to draw a box with a square base, and it has an open top. Okay, so it doesn't need to be a great drawing. You don't have to be Picasso to draw a good drawing of your box here. We just need some passable box. So we're going to get a box type shape here. Okay. And we know that we have an open top here. So this is a bit of a harder thing to show in a drawing. But we do want to keep in mind that the top is open. So we don't have to worry about basically the cardboard that's going to be needed to fill in the top of the box because the top is open. So all we really need to kind of think about here is the cardboard that we need to build basically the four sides of the box and the bottom of the box. Okay, so we don't have to worry about this red face, the top of the box. We can ignore that. But what we want to do at this point is label our drawing, like I said. So let's just go ahead and say that we're going to, keep in mind, we know that our box has to have a certain volume, but that means that volume is not the quantity that we're trying to optimize, right? The quantity that we're trying to optimize, which means find the maximum or minimum of, is the amount of material used. So the amount of material needed to construct the box is basically the surface area, the amount of cardboard we need to build these four sides and this bottom. So what we want to actually optimize is surface area. So I'm just going to go ahead and call that S. Actually, I'm going to call it SA because S sometimes looks like a 5 when it's by itself. So I'm going to say SA is our surface area. And we need to come up with an equation for this. So again, what we're going to have to kind of use here, what we have to figure out at this point is what are the other measurements that we have to use to find the surface area? Well, it is a box. We're probably going to want to use the length, width, and height of the box to find its surface area. Okay. So in general, surface area is going to use the length, width, and height. However, there's one other key piece here that this problem told us that we can use to simplify this a little bit further. Because if we were to go straight to surface area from here, using length, width, and height, we end up with a 3-variable equation. However, notice it says right here, we have a square base. What does that mean? That means that the length and the width are going to be equal. In order to have a square base, we need this side right here and this side right here to be the same length. That is going to create a square on the bottom. So instead of thinking of length, width, and height, we can actually just eliminate one of these letters since we know that they're going to be equal to each other. We know that this side length is going to be the same as this side length, which is also the same as this one here and this one. So all four of these sides down here at the bottom are going to be W. So now to find the surface area of this box, let's think about this box has 5 faces, right? We have the 4 sides and the bottom. We don't have a top. So the surface area is going to be the sum of all of the areas of these 4 rectangles and the square base. So the square base is going to have an area of W times W, so W squared. And then each of the 4 sides of this rectangle is going to have an area of H times W, right? Because it's just a rectangle. Height times width is going to give us the area of that. So we're going to have plus W times H. Now that's just one of the 4 sides. We have 4 of these sides. So 4 times W times H is going to be the total surface area of this whole box. And again, we don't have a top, so we don't have to worry about that face. So these 5 faces are going to add up to this surface area. So this is the equation that we need to optimize. Okay. So then the next step was to come up with our restriction equation. What does this problem tell us about how these different quantities have to be related to each other? Well, this is pretty much the only restricting information we have. We know that the volume of the box has to be 32,000 cubic centimeters. So what that tells us is the volume of this box, the volume has to be 32,000 cubic centimeters. What is the equation for the volume of a rectangular prism? It's length times width times height, right? So the length and width and height of this box are H, W, and W. So the volume of this box in particular is going to be H times W, which is the same as H times W squared. So we know this is the volume of this particular box. So let's just call this volume of this box volume 0, volume naught. In order to, okay, so I'm sorry. What we know is that the volume of this box, this V0, has to be 32,000. So we know that 32,000 equals h times w squared. Okay, so now we have our restriction equation. We have the equation we need to optimize. So now what we can do is we can use our restriction equation, solve for one of the variables. Doesn't really matter which one you pick. Let's just go ahead and solve for h. To solve our restriction equation for h, we would just have to divide both sides by w squared. And that would give us h equals 32,000 over w squared. Okay, so now what we can do, since we know this quantity here is equal to h, we can go back up to the equation that we are trying to optimize, the surface area, and we can replace our h with this quantity here, 32,000 over w squared. If we do that, we find out that our surface area is going to be w squared, which we already had here, plus 4 times w times 32,000 over w squared. So plus 4 times w times 32,000 over w squared. Okay, now let's just take a moment to simplify this equation. So simplifying this, that w is going to cancel with one of those w's, just giving us a w there. So we're going to have w squared plus 4 times 32,000, which would give us 128,000 over w. Yeah, because 30,000 times 4 would be 120,000 plus 8,000. Yeah, perfect. So now this is going to be our surface area. And now look what we have. We have an equation for our surface area, which is the thing that we're trying to minimize. And we have it just in terms of w. It's a single variable equation at this point. So now once we've done that, we can move on to finding the actual absolute minimum of this equation. So to find the absolute minimum of an equation, first we need to find its derivative. So we're going to find the derivative. We'll call it SA prime. Before we do that, though, let's think about how we can rewrite this equation, because having something over w doesn't make it very easy to find the derivative of that function. So instead, what I'm going to do is write this as 128,000 times w to the negative 1 power, because w to the negative 1 is the same as dividing by w. So now to find the derivative of this function, we can just use the power rule. Power rule says we're going to bring this 2 down in front, and then minus 1 from the power. So that's going to give us 2w to the first is just 2w. And then again, power rule here says we bring our power down in front, multiply it by the coefficient. So instead of plus 128,000, we are now going to have minus 128,000. And then keep our base w as w, and then minus 1 from the power. Minus 1 is minus 2. Okay? Now I'm just going to put this back into a fraction because the next step is going to be easier with it not being in a negative power. Okay. And then what we need to do in order to actually find our critical numbers, the places where our absolute minimum might occur, is by taking our derivative and setting it equal to 0. Okay. We also, in general, to find critical numbers, need to consider where our derivative would not exist. Looking at this function, there's only one place where we need to, or one thing that could happen, I should say. Actually, yeah, one thing, sorry, that could cause this derivative to not exist. And that is if the denominator of this fraction equals 0. Because if that happened, we would be dividing by 0, which is not okay. You can't do that. The only thing that would cause this denominator, w squared, to equal 0 is if w equals 0, which if we go back up to our drawing, w equaling 0 does not make sense because the width of our box would be 0. We would not have a box. So we can ignore w equals 0 because that's not even within the domain of what w can be. So you always want to be careful to think back to the real world example of what this equation represents and make sure that you're plugging in numbers that actually make sense based on the situation. W equals 0 makes no sense. And that's the only place where this derivative, SA prime, would not exist. So we only need to worry about where does SA prime equal 0. So we can solve this equation for W to find that critical number or critical numbers. So first thing we'll do, we'll add 128,000 over W squared to both sides. Okay, then we can multiply both sides by W squared so that we can get rid of our fraction and just have everything on one line, basically. So that's going to give us 128,000 2W cubed divided by 2. And that should give us 64,000 equals W cubed. And then we can take the cube root of both sides, giving us W equals the cube root of 64,000, which you can just plug into a calculator. However, I believe, no, that might not be a cube number. But anyway, whatever this number ends up being, the cube root of 64,000 is going to be the W that gives us our critical number, which is going to have to be, typically what you would probably want to do from here is confirm that that is an absolute minimum. Based on the context of the problem, that critical number should be an absolute minimum. There shouldn't just be one critical number that creates a situation where we're using the most possible cardboard to make this box. It doesn't really make sense. So we can just go ahead and assume that the width of the cube root of 64,000 should be the place where we minimize the amount of material used to make a box of this this volume. Now, do keep in mind units. This is in cubic centimeters, so this is going to have to be in centimeters. So the units here are going to be centimeters, and that should be the width that gets it to us. So keep in mind, we do want to find the dimensions of the box. We're not quite done yet just because of what the problem is asking us to find. They want us to find the full dimensions. Well, we found this equation here, H equals 32,000 over W squared. So we know our W, so we know the length of the base of each of these sides here. We know that those are both going to be the cube root of 64,000. Then to find the height, all we would have to do is plug the cube root of 64,000 in for W here. So that would give us 32,000 over the cube root of 64,000 squared. And this is going to be the height of our box. And then the width and length of our box is just the cube root of 64,000. So I'll let you plug those into a calculator to get your actual final number there. I think it'd be fine to leave this in exact form, assuming that 64,000 is not a cubic number. And if that's the case, then I think this is a perfectly fine answer. You could probably do a little more simplification from there, but I'm not going to do that. I'll leave that for you. So that's all I had prepared for you today. I hope you got some use out of this. If you did, do me a favor and hit that like button down below. It's a huge help to my channel so I can keep making more videos like this. And if you did get some use out of this video, hit that subscribe button and that bell icon down there too, because I'm going to have plenty more videos coming out that I'm sure that you will find helpful too. So thanks for coming. Hope to see you next time, and have a good rest of your week and rest of your day.